Welcome to ITProTV. You're watching the CompTIA IT Fundamentals for exam FC0-U61. I'm your host, Ronnie Wong, and today we're going to be diving into the world of programming and taking a look at programming concepts. And here to help us to understand this a little bit better, of course, is Mr. Don Pezet himself. Don, welcome to the show.
Thanks for having me back, Ronnie. And like he said, we're going to be diving into programming and development. If you are new to IT and all you've had exposure to are the movies and television, then you know that development is where the money is. It is quite the buzzword today, and it is, I don't want to diminish it, make it sound like it's not important. It actually is really, really important because we all rely on software, and somebody has to make that software. Somebody has to write the software, and that's what a developer does, or developer, engineer, programmer, coder. You hear all these different terms, but it all amounts to the same thing. And that's somebody who makes software, somebody who makes programs to do stuff. So have you ever wondered, how do they do that? How do they make a program that does stuff? Well, in this episode, we're going to try and answer that question. We're going to show some of the basics of development, how applications are written, kind of give you guys an idea of the logical workflow. Now, I'm focusing on basic concepts and ideas in this episode. If you want to see how an application is actually written, in the next episode, we'll tackle a true programming language. We'll use Python and we'll write an application. But in this episode, we're going to focus on the concepts, how applications are developed, and some of the things that the developer goes through while they're doing their job.
All right, Don. Now, I've watched Mr. Robot enough to know that coding seems relatively easy. The guy can actually, type lines of code amazingly quickly. But Don, what is code and how do we really get it written?
All right, so code is actually just short for source code. Source code is really just a list of instructions that you feed to the computer to tell it to do something, right? Think of it as like you have a kid and you're trying to get them to bed. I go through this every night where I tell my son, you need to brush your teeth, put on your pajamas, go to bed, right? It's a series of instructions. And then he's my little robot. He goes and he does his job. Well, if he chooses to, right? Much like a program, it's supposed to work if it chooses to. So I give it a series of instructions and off it goes. The computer does what I tell it, right? But how do we give it those instructions? When I tell somebody to do something, go brush your teeth, I'm using English, right? The English language, that's what I speak. Computers don't speak English. In fact, computers speak a very low-level language. It's called assembly or machine code, where that's the language that the hardware speaks in the background. Well, we can't speak that as humans. It's too difficult. It isn't a way that we normally think. So instead, what we do is we rely on a computer language. Computer languages are a lot like learning a foreign language. If I were to go to France, people would expect me to speak French. And I know how to order a cheeseburger at a restaurant, right? Well, I know how to do it in English. But if I'm in France, I need to say it in French and order the cheeseburger. It's the same action, right? I'm just using a different way to phrase that. When you look at the source code of an application, all a source code is a list of commands that are just written in a different language. And when I say a different language, it's typically English, right? English is the kind of de facto language of application programming. But the sentences, they don't read like English. They're English words, but they're arranged in a very different way. And the reason is it's being put into a way that the computer can understand. That's really what programming is, right? Everybody in the planet could be a programmer if they just knew how to speak the language. I might say, you know what? I really wish there was an application that could track golf scores. Okay, well, what's involved in that? All right, well, I need a little gray window with a box, and I need 18 numbers because there's 18 holes, and I need to be able to enter in a number for each one of those. Okay, well, I just wrote a program, right? I'm coming up with the specifications for that program. But now somebody's got to sit down and figure out, how do I tell the computer that? How do I make the computer understand what it is that I'm trying to get it to do? And that's done with source code. We start typing out those commands and saving that into a file, and the computer can take that and then perform that action. Now, the computer understands what's called machine language, or the processor, the memory, the hard drive. They all have a language that's embedded and built into them that is far too difficult for us to write. Right? Now, there are some special languages out there like assembly that let you write that way, but it's very difficult. So what we're normally doing is using some kind of intermediary, a language that sits in between our English and the machine code the computer expects. And that intermediary language tries to meet us halfway, right? halfway to being plain English and halfway to being machine code, and make it a way that's understandable for us. So when we pick a language, we're picking one that we can at least do as good a job with as far as speaking, right? And then that language will get turned into the machine code on the back end that the computer understands, and now we've got a way to tell it what to do. That is ultimately what source code is. So it's not as complex as it seems, but it is very similar to learning a foreign language.
Now, Don, you seem to be hinting at the very fact that there are different types of languages then. So it's not just saying, I want to write something in this and then the machine will be able to pick it up. I have to actually pick a type of language that I need. So what types of languages are there?
Oh, there's actually a ton of languages. If we were to try and list off all the different programming languages, we'd be in front of these cameras for a while, right? So let's not think about an individual language, but more like a category, right? Languages fall into categories. And the two most common categories that are out there are interpreted and compiled languages. Okay, interpreted languages are languages where I write the source code. So I write out code to do something, and then I use what's called an interpreter to read that code and perform an action, right? Let me give you an example here on my machine. So I've got a simple little application that I wrote this morning, and it's called hello.py, right? It's a Python application. And I wrote it, so it is just the source code, which it's super simple application. If we take a look at what is in there, let me just edit the file so we can see it that way. If we take a look, sorry, not hello.py, interpreted.py. That's the one that I wanted to show. Sorry, I'm pointing at the wrong one. If we take a look in there, it just has one simple line that tells it to do one thing. I want to print on the screen. This is an interpreted program, right? The print command is a Python command that says display something on the screen. Now, on the computer side isn't thinking print this on screen. It's thinking, all right, there is a hardware monitor that is plugged into this port, and I need to put something in this place in the video card's RAM to make that display on screen. That's really complex. But print this text, that's really easy, right? This is the easy human side that I get to see, and then on the back end, it gets to do all that hard stuff and actually display it. Now, when I write this, it's written in the language, very simple, it's right there on my screen, and it's ready to be run. But I can't actually run this by itself. It's not a true program. It's a set of instructions. I need to use an interpreter to read these instructions and then execute them. So if I get out of that and I want to run that program, I would need to call an interpreter. I wrote this in Python, so I'm going to use the Python interpreter, and I'm going to feed that file into it. And when I do, it runs it, and it outputs on the screen. This is an interpreted program. The program just executed, and it ran, right? That's an interpreted program. These are really nice because you just write your program, and then you can test it out. And if you want to make a change, you just make a change real quick, and you run it, and so on. You keep going over and over and over again. That's how interpreted languages work. And there's a number of languages out there that are interpreted. Some of the most popular ones, well, Python, that I just showed you. Python is very powerful for darn near everything. It's a very versatile language. And you'll find most people recommend it if you're just starting out, if you're just learning. It's a great language to start with. There's also Perl, which is a language that is great for scripting and automation. Automation is when we have some kind of administrative task that we perform, and it's the same task over and over and over again. You could just write a Perl script that goes in and does that task for you. So if every Tuesday you're having to download a file from some site, you can write a Perl script and have it download from that site every Tuesday. It just makes it automatic, right? There's also other popular languages like PHP, which is used for web page development. A lot of web pages are written in PHP. And then JavaScript, actually tons of websites. If you go to the ITProTV website, the bulk of our website is written in JavaScript. These are interpreted languages. Somebody writes the script, and then when the server actually renders the page, it's having to render it, it's having to build it into the final product that gets delivered to the end user. Right? Those are interpreted languages. The alternative are what are called compiled languages. Compiled languages are ones where you write them in a particular language, and then instead of an interpreter, you run what's called a compiler. And the compiler is effectively changing whatever language you wrote it in into a different language, a language a computer can understand, which is typically machine code. And when it does that, it makes the program far more optimized, significantly more optimized than what it was when it was an interpreted language. With an interpreted language, it's having to be built every time it's run, right? Imagine you wanted to get a car to go to work, right? But when you get the car, it's all in pieces, 1,000 pieces. And you got to put the 1,000 pieces together and then drive to work. And then the next day you get up in the morning and the car's back in 1,000 pieces again. And every day you've got to put the car together and then drive to work. With a compiled language, you put the car together and it stays together. It's assembled, it's built, and anytime you need it, it's already done. And that means it's significantly faster, all right? The problem with compiled programs, the negative side, is that anytime you make a change, you've got to recompile. You have to rebuild it, right? So what I showed you a moment ago was interpreted. I also have one that is compiled. And this is one that I wrote, and then I compiled it using a C compiler, so it's actually compiled in a different language. But once it's compiled, it's now ready to run. And I'm running Linux here as my operating system, and you'll see where it's showing that that file is green because it's an executable. This interpreted.py file that I ran the first time, it's just a text file. It's just text that is a series of instructions that the Python interpreter read. But this one is an actual program. It's a program all by itself. It doesn't need an interpreter. It's already been built. Now, when I run it, when I call that compile.py file and I run it, it outputs on the screen. This is a compiled program. All it had in it was one line, print, and then that word right there, just like the other one, right? But let's look at the differences. The first difference you can't really see, and that was how fast it ran. Both programs are really small, but on larger programs, you'll often see a performance difference of about 300%. Generally, compiled applications run significantly faster. And that's because the work of assembling, of putting it all together has already been done. It's already done, so it's ready to rock. If you have a massive program like Microsoft Word, if it had to build that every time you launched it, it would take forever. It would be the slowest program on the planet. But having it already built up, it launches right into memory and off you go. It still might not be the fastest thing on the planet, but it's significantly faster than if it was interpreted. All right? So on a positive side, you get performance. On a negative side, let's say I look at this and I say, oops, I spelled compiled wrong, right? Well, if I spelled something wrong, I need to go and edit it. In an interpreted program, I would just edit the text file. Edit the text file, and then you run it and you're in business. But with a compiled program, I would have to edit the source code and then recompile it. See, if you look at that file, compile.py, if I edit that file and I open it up, when I wrote it, it was just text. And it said, print, this is a compiled program. That's all it said. Now, if I look at it, though, I get this. I get a whole bunch of mess, right? And that's because it's been compiled. And as I look at it, I might see some things in there that look like I can read them. Like here's a library that's been linked inside of it, right? So I can spot some things. But for the most part, it's binary data at this point. It's binary data that the computer expects, not that a human expects. It's been assembled in a way that's designed for the computer to read it, right? And that makes it faster, and it also makes it more portable. I can take this file and I can copy it and give it to somebody else, and they can run it. The program will work on their system as well. So that's a compiled application. These applications are usually a little more difficult to write in, but they're usually a lot more powerful. And this is where we find languages like C and C++. Those are compiled applications. There's also some other ones like F# and others that are a little less popular. But C++ is usually the primary example of a compiled language. So those are the two main categories. And as we talk about programming and code and development, it's usually those two that people mean. I mean, one or the other, right? But there's actually even other ones. In fact, if you've been watching this series, we haven't gotten to it yet, but we have a section on databases. And when we get into databases, they have their own language they use called the structured query language, or SQL. It's a query language. Query languages are how we talk to databases. If I want to ask a database something and I say, hey, give me the contents of a table, I would say something like select star from, and then whatever the table's name happened to be, like that. That's a language that they use to talk to those databases. SQL is not compiled. It is interpreted, but it's not interpreted like a normal programming language. It's interpreted by the database server, which then executes it and performs some kind of an action. So, for example, if I wanted to display something on the screen like hello world, I would say select, and then I would tell it hello world, and the database server would know to return a table that contained that information. It's just a different language, right? Same idea, but a different language. The last one, which I've already mentioned, is assembly itself, right? You don't have to use a regular language. You could say, you know what? I'm more than a human being. I can think like a computer. If you can think like a computer, if you can, deal with that at a hardware level, you can skip the whole crazy intermediary language and actually write in a language that's called assembly, or sometimes people call it assembler. Assembler is the actual compiler that it uses, but assembly is the language. And it also gets abbreviated as ASM sometimes, so you'll see that as well. But when you write in assembly, you're actually writing instructions to talk directly to the hardware. And let me tell you, it is really, really hard because there's so many different types of hardware that are out there, and to account for all of that, and to understand how to talk to it is really, really challenging. Engineers usually will do this, but regular developers will not. Because it's so difficult, it makes troubleshooting harder, it makes writing it more difficult, it takes longer to develop in. But it is worth it because assembly is the fastest of the languages, because the applications are written specifically for that hardware, for your processor, for your memory, and so on. It's written for your hardware, and so it's considered to be one of the best ways to write an application. Well, the thing about assembly is that it's typically used for hardware vendors. If you write or not write, but if your company manufactures video cards or sound cards or whatever, and you need to write drivers, a lot of those will end up being written in assembly. The core of your operating system, your kernel of your OS, a lot of times those will be written in assembly. Not all, though. Like in Linux, the kernel is actually written in C, so it's just written in a compiled library, compiled language. So it's not always going to be one versus the other. It usually comes down to some degree of choice, right? When people choose a language, and maybe I've got a particular reason for one, or maybe it's up in the air, who knows? But I've got a lot of choices, right? So those categories, really interpreted and compiled, those are the two most common. And then after that, you have things like query languages and even assembly or machine code. Those are all just different types of languages that are out there.
Now, Don, giving us this whole list of different types of languages out there, how do I know what to choose as a language then if I wanted to write something?
Ronnie, I wish there was an easy answer to this one. It's super subjective, right? You'll find that you can achieve practically anything with any of the languages. So if you just blindly picked, just like opened up a book of programming languages and randomly stuck your finger and picked one, then you could pretty much do everything you wanted, right? All the programming languages are very robust and very powerful, but a lot of them are designed for like particular environments. For example, PHP. PHP is really designed for web pages. If you're developing a web application, PHP works great. But if I'm trying to develop a driver for a video card, PHP is not going to work great. I could force it. I could probably make that work, but it's not designed for that. It's not ideal. So normally we choose a programming language based on a particular need. Or we go to college, and in college they force you to take a couple of classes in a particular language and you learn it and you're used to it, and so you just stick with what you're used to. Again, there's nothing really wrong with that as long as the language is able to achieve what you want. A lot of colleges will teach C++, it's a very powerful compiled language, a great one to learn. They'll teach Visual Basic, which is not so great anymore. A lot of that's been replaced. Even Microsoft has moved a lot of that over to C# and other languages. But colleges will still stick with VB because it's so easy to learn. It's a very easy programming language to jump into. You'll see that sometimes where schools, universities, they'll pick languages not because they're the most powerful or flexible, but because they're the easiest to teach with, to teach individual components. Languages like Eiffel are used in a lot of colleges and are never used out in the real world because they're too clunky, they're too slow. And if you want to write applications that are fast, that's not going to work for you, right? So you'll end up switching over to other languages. Now, in today's world, if I were just getting started today, I was 18 years old, right out of high school, and I want to get into IT and I want to be a developer, web applications. Web applications are really where everything is at. So learning languages like JavaScript and Python, those are going to be two really, really popular languages that make it extremely easy to go out there and find jobs and careers. So those are really good right now. Will they stand the test of time? Probably not, right? In another 10 years, maybe JavaScript will be dead and people have moved on to something else. Other languages like C++, people have been writing C++ code for over 30 years, and it's still considered one of the most rock-solid, stable languages that's out there. So that's one that they say if you can learn C++, you can learn anything. So if you start with that one, then you're kind of set up to be very very good down the road. But most people learn more than one language. That the concepts of development are actually the same across all the languages. So switching from one language to another is just a matter of learning the commands. Once you know the concepts are the hard part. Once you understand the concepts, the language really doesn't matter anymore. So it's not. It's kind of hard to go wrong when it comes to picking a language.
All right, Don. So let's break down to the final question here as far as this goes in the different languages. How do they actually work then?
All right, so the languages, I mentioned earlier, they're like a series of commands, right? Well, you have to know what those commands are, first off. And you have to know the order of the commands that the languages expect. And so each language has a definition that defines exactly how they function. And at the end of the day, what they really do is they function like a flow chart, right? If you've ever seen a flow chart where it says like, did the product work properly, yes or no? And if it's yes, then you go to the end, right? And if it's no, then which part failed? Was it the air conditioning system, yes or no? And if it's yes, it goes to the air conditioning part. And if it's no, it moves on to the next. Was it the transmission? And so on. You've got a troubleshooting flow chart. Well, applications work the same way. They display a screen. And then it's like, hey, did the user click button 1 or did they click button 2? If they click button 1, it opens a new file. If they click button 2, it closes the program. You're just defining a sequence of events. And you're defining them in the way that that language expects. But the sequence of events are, like I said, they're the same for each language. So if you have where you print something on the screen, if you take user input, either a button press, a click, typing letters, if there's a loop where I'm cycling through something over and over again, I just have to tell it to do that. I have to tell it each of those steps along the way. And the more complex a program is, the more work that takes. All right. The program that I showed you a moment ago had one line. Print, this is a compiled program. That's it, one line, right? Microsoft Windows has over 1 million lines of code. That's a lot. And it wasn't written by one person. It was written by thousands of developers. Microsoft has more developers on staff than anything else. And, well, I don't know, they might have more salespeople, who knows? But they have more developers than most companies ever dream of. And they're all working on different pieces of Windows. There's a whole team of developers who are dedicated just to the start button on the screen. And that's because it's so involved in your average workflow. So when you develop a product, the more complex the product is, the more people you'll need working with you to get it done. But when you're a one-person team and you're creating a simple application, you can grasp it all yourself, and you come through and you write the various things that you need done, and you tweak it, adjust it over time, and finally end up with a well-rounded product.
All right, Don, I know that you really want to show us at least a basic idea of an example of how programming works, but noticing the clock, we are out of time for this episode, and that means, if you don't mind, we'll come back for a part 2, and you can show us an example of what we want. So, Don, last words for at least this first part.
All right, so what I want to do, and I'd hope to get to it in this part, but we'll do it in part 2. I want to show you how to build an application. But I want to do it without the programming language in the way first, right? So we're going to conceptually go through and we're going to build an application. It's going to be exciting. We'll make a little cat walk back and forth on the screen. But we'll get a chance to see that so that we can understand exactly what's going on inside of an application. And then we're going to come back after that and we'll write an application in Python. We'll actually develop one in a true programming language and write it out and get a chance to see how that works. So kind of doing the baby steps as we move through it. So definitely stay tuned for part 2 where we'll see the concepts. And then in part 3, or not part 3, it'll just be its own episode. We'll actually write one in Python.
All right, Don. Well, thank you for leading us this far. And don't forget, you want to stay tuned for that part 2 coming right up after this episode as well. So signing off for ITProTV, I'm your host, Ronnie Wong.
And I'm Don Pezet.
Stay tuned right here for more of the CompTIA IT Fundamentals Show.
Thank you for watching IT Pro TV.